Vijay and I work at IBM building a Java distribution called IBM Semru Runtimes. And like lots of companies that build Java distributions for their customers, like Amazon or Microsoft or even Oracle, we work to build this Java distribution in support of our products and services and customers and support their needs when they're trying to run Java-based workloads. And like lots of those businesses, everyone is at all kinds of stages of development in terms of their journey to cloud. Some of them are right at the beginning. They're working with huge monoliths. Some of them are at the end. They've already transitioned to very small microservices. But when we're looking at trying to support this immense spectrum of Java workloads, we really have to be careful to focus on or be able to deal with all of the requirements that come from all of this varied support. So we're going to give a little bit of a different talk today than we would normally give. Normally we would be here talking about a particular technology and telling you how it's fantastic for improving some particular performance metric. What we're going to try to do today is give you a very full explanation of a lot of the different technologies that are present in IBM Semru runtimes that we've been building for the last 20 plus years, and show how they all fit together to address various performance, provide various performance advantages and also disadvantages, and how they work together to mitigate their own disadvantages. And so as part of this process that we're trying to leave no Java workload behind on this journey to cloud. We want to be able to support everyone. And in fact, as we'll try to make the point during this talk, it's also important to focus on many different performance metrics and make sure that you're not ignoring any of those metrics either. Our lawyers are always concerned that you will think that we're giving you product roadmap information or talking about future product plans. We're not. Don't be confused about that. And they're also concerned that we might say something wrongly. So everybody owns their own trademarks. Don't worry about any of that. So just a brief introduction. So my name's Mark Stoodley. I'm a senior technical staff member and the chief architect for IBM Java. So I oversee a team on 3 different continents that develops IBM Semru runtimes. Vijay, my colleague here, is also a senior technical staff member, and he is the IBM WAS and Java perf architect. We both work at the open source projects OpenJ9 and OMR, which will come up a little bit briefly later in the talk. The outline of the talk is we're going to give a quick refresher on what Semru runtimes is and how it's built and powered using the Eclipse OpenJ9 Java virtual machine. The bulk of the talk is, and then I'm going to talk about the problem space for Semru runtimes and try to explain the complexity of the problem space that we're trying to deal with, as well as all of the performance metrics that we're trying to solve for. And then the bulk of the talk is actually going to be this third part where we'll talk through all of the improvements, well, not all, but a good selection of the major improvements that we've made in Semru runtimes over the years and show how they fit together to address various performance gaps. So, start off with Semru. So, Semru runtimes is an open source JDK distribution that IBM builds. It's built from the Eclipse OpenJ9 Java virtual machine. In fact, it is the only Java distribution that I know of which uses the Eclipse OpenJ9 JVM. This was open sourced by IBM about 6 years ago, and it is the source of a lot of the performance improvements that we're going to talk about later in the talk. Other than that, it is an OpenJDK distribution, so it takes class libraries from OpenJDK, virtually unmodified, so you have a nice consistent Java interface. It's plug replaceable with other JDK vendors' JDKs. IBM builds it, we make it available. There's 2 editions, doesn't really matter too much. One of them has an open source license, the other one has an IBM license, and one of them we've run the Java certification tests, and one of them we haven't. We run copious quality testing using the Eclipse Adoptium project before we would release anything. It's very easy to get, although we primarily invest in IBM Semru runtimes based on the needs of our stakeholders and our product and business. Building Java isn't our business. It's not our business to make money from Java, so we make it available publicly because it is open source projects that we're working in anyway, and it's very easy to get. And it's, even though it underpins thousands of Java-based IBM products and services, we make it available for free, even for production use. So there's lots of different ways to get it. All right, we've already gotten through one of three, so it's good progress. Let's talk about the problem space that's facing these SEMRU runtimes. So as I talked about earlier in this journey to cloud, there's a lot of pressure on the applications that we used to build, say 10, 15 years ago, which are large-scale monolithic applications that ran on very full-featured application frameworks, and they're very heavyweight. And over time, we've been pushing towards using more lightweight frameworks and runtimes. We've been refactoring applications into macroservices and microservices, and at the extreme end, we have seen the rise of functions as a service and all of these things running in serverless environments. So as a team that builds a Java distribution that's going to be used by our customers, we have to ask ourselves, what should we be focusing on in this space? And unfortunately, the answer is that we can't really ignore any of them. And I'll try to explain why that is. So to start off with, though, there's so many variables here. So we have, what application style are our customers using? Are they using monolithic apps? Are they using macroservices, microservices? Are they using serverless? Are they doing functions? Unfortunately, the answer is yes to all of those things. And in fact, at the scale of IBM and the number of customers that we have and the number of products we have, there's usually somebody who's going to get upset if we don't help them with something that they need done in any of these spaces. So we can't afford to say no to any of these. And unfortunately, this is only one of the variables that matter, right? You could look at across all of the different deployment scenarios and configurations that we have to use. Are they running on bare metal? Are they using hypervisors? Are they using containers? Which container framework are they using? Are they running with Kubernetes? And then which hardware platform, which operating systems are they using? Which Java versions are they using? Every single one of these, somebody's going to say yes. And if you don't help them, somebody's going to get upset. And finally, there's the question of what performance metrics matter. So how do you make Java workloads run better? What does better mean? Does better mean faster? Does better mean less memory? Does it mean starting faster? There's lots of different questions here. And I want to focus on this one a little bit because it's going to be very important for the rest of the talk. So I'm going to make the argument that there's lots of possible metrics that people care about. Well, it's not really an argument. People tell us that there's lots of metrics that they care about. And so we need to be very flexible on how we work on IBM SEMRU runtimes. The key performance metrics that we hear about are things like startup time. And I define startup time as the time from when you start your Java process to when you've gotten your framework initialized and you're ready to start processing transactional workload. Memory footprint is usually the resident set size that's being occupied by the Java process as it runs. There's lots of ways of measuring footprint. You could measure it after startup. You could measure it while you're running load. You could measure average footprint. You could measure peak footprint, etc. Ramp up time, to differentiate from startup time, ramp up time is once you're starting to process customer transactions, you're starting to exercise the code paths that actually handle the workload that your customers are asking you to do, until you reach steady state. So as we all know, things need to be initialized, code needs to be compiled, etc. And so you have this ramp up curve of time over time where your performance rises as you fill in caches and so on. Response time, I think everyone probably understands, it's how quickly are you responding to transactions. CPU consumption is kind of like memory footprint, except it's how much CPU are you consuming. And again, you can measure it at a point in time after startup or while you're handling load. You can do average CPU consumption, you can do peak CPU consumption, or you can show CPU consumption over time. So one thing that's important to take away from this is that when you read a blog article or read about somebody making a performance statement about footprint or CPU consumption or any of these metrics, you have to be really careful to make sure you understand which metric they actually mean and what they're actually monitoring when they talk about these things, because it's very easy to draw incorrect conclusions based on which footprint you think they're talking about versus what metric they actually measured. Now, different workloads, different deployment patterns may emphasize different metrics, right? If you're starting lots of little short-lived Java applications, then you might care a lot about startup performance and not very much about that steady state performance. On the flip side, for monoliths, you care a lot about steady state performance because they're going to be around for a long time. And the point that I'll make is that optimizing to improve one of these metrics often means you have to negatively impact other metrics. So it's not a free, there's no free rides here. You can't just say, I want everything to be better and get it very easily. It's a very tough process to get there. And we're going to show you that process that we've gone through to try to push out on all of these metrics to make all of them better. But it's really the case that there's no single answer here. And we need a very balanced approach. Oh, and one other point that I'd like to make is that it's really important to measure all of these metrics in the same run at the same time, right? So again, if you're reading a blog article that says, yes, I can make memory footprint very small, you better be making sure that they're making memory footprint small without affecting throughput, because it's easy to use less footprint if you do less work. All right. So I wanted to put a few diagrams in front of people just to give this a bit of a pictorial representation. So I call this a kind of pencil diagram because it obviously looks like a pencil. So the red tip of the pencil is that startup time that I talked about, where you're initializing the application framework, but you're not able to handle any load yet. The orange section there is the ramp-up section, where you're starting to handle customer load, but you haven't really gotten to peak performance yet. And then you have that nice green steady state one that everyone likes to see and that wants it to be as great as possible, right? So over time, the reason why it kind of grows out is you haven't, at the beginning of this diagram, you haven't seen all of the program yet. By the time you get to steady state, you've seen everything and you've compiled everything. Now we can look at a few different performance metrics here. So responses per second, that would be normally a kind of a throughput kind of a metric. And you can see during startup, because you haven't initialized your framework yet, you can't handle any load. So there's no way you're responding to anything at this point. You are doing no work that helps your business at that point. During ramp up, you're still initializing the code paths that are being used to handle the transactions. And so at this point, you're starting to get responses per second, but you're not at your peak, like I talked about before. And then finally, in steady state, you have reached your steady state performance. And that's going to vary with load, but obviously I've simplified things here to just show a constant load. If you look at some of the other metrics, like some of the cost-related, overhead-related metrics, like how much memory are you using, like, for example, resident set or CPU consumption, you can see that during startup time, there's actually quite a lot of overhead that you're paying in that section. And that's because the JVM's starting up, the JDK's starting up, your application framework's starting up, you're initializing a lot of different components. You're very heavily focusing on work to get up and running. And then during ramp up, you're doing the same kind of thing, but with different code paths, the code paths that are responsible for processing transactions, filling in caches, etc. So you're doing a lot of overhead during these early phases. And then, finally you kind of get everything compiled, all the caches get filled in, and everything kind of settles down, and you get this, the green curves in the steady state section. So traditionally, Java runtime technology, if you go back 10, 15 years, traditionally the focus of Java runtime technologies has been in this steady state, right? When people say they want the performance of Java to be better, they focus on steady state performance. And it doesn't really matter how long it takes to get there because, people were working on monoliths, right? And monoliths spend most of their time in that steady state section. Yes, they might take a while to start up and ramp up, but once they get there, they're probably going to run for hours or days or months even. So that focus on the steady state time was the right choice for most Java runtimes. But the way that things have been moving in this journey to cloud is really starting to put pressure on the other parts, the other phases of execution. So if you look at a Java workload that gets refactored into many micro or macro services, you can see that now we have a lot of different JVMs running. They all have this sort of startup, ramp up, and then steady state performance aspect. They all have the same overheads in terms of memory and CPU usage. But now we have many of them. In fact, we might even have multiple instances of the same service running in the same world. So we have this extra pressure on startup and ramp up costs and compared to steady state. And so it's becoming more important to invest in these areas. If you move to a serverless model, now you start seeing instances that are popping up and down in response to how much load there is. So you might see a service A, which has kind of a constant workload, and it's just kind of, there, and it runs and it does everything that it does. Here you've got service B, and the workload for service B might be changing quite a lot. So, you've got one sort of base service that's handling a certain amount of workload, and then you get a spike and another instance has to get started up, but it doesn't last for too long. And maybe you got even a wickeder spike, and you had to start a third instance briefly, but that spike didn't last very long, so the instance then went away. These kinds of effects are now placing even more pressure on the overheads for startup and ramp up, because now you don't have necessarily a steady state section even to get that payback. And when you go to the extreme end of functions of a service, now even if you have some reuse, it's still not usually a lot of reuse, and so the time that you spend in steady state is not very much. And if you're only running one function, there almost isn't a steady state. You almost don't have that green. So the costs are really a lot higher. So why does all this matter, you're probably thinking to yourself. First of all, there are some financial implications for deploying Java workloads, right? The resources that you use in the cloud and in on-prem deployments, they cost money. Right, so the more cores that you use, the more cores you use, the more you have to pay. The more memory you use, the more you have to pay. In fact, in the cloud, if you want twice the memory, you're probably going to be paying twice the amount for each instance. And I know this is very obvious to everyone, but I just point it out because it's relevant here. Every dollar that you spend on infrastructure takes $1 of revenue out of your pocket, right? You invested all that effort to get that $1 of revenue, it's gone because you had to pay for extra infrastructure. So you don't want these extra costs. Now, startup and ramp up, as I showed on the previous slides, they both represent very heavy resource usage, but provide less than full value. So they're not great from a business efficiency kind of standpoint in terms of how many customer transactions are you handling. And some of the architectural styles, as I pointed out, put more pressure on those overheads. So they become less efficient if you aren't focusing on how to improve those aspects of a Java workload's execution. Because we now have lots of microservices and run in serverless models, we're collectively probably using more memory for all of these different JVMs than we were using in a big monolith, despite all of the advantages to writing things in microservices. There's also technical implications of all of this for similar runtime. So bringing this back to what Vijay and I have to do on a daily basis, getting our team to make things better, the implication in this space is that accelerating or reducing those overheads in the startup and ramp up, they require different tools than have been built traditionally or different approaches than you would use to attack that steady state performance. So let's look at startup. As I mentioned, startup is the time when you're initializing lots of components throughout your application framework. So you're hopping from component to component, running a bunch of code that initializes it, running a bunch of code that initializes it, running a bunch of code that initializes it, and you don't get a whole lot of reuse. Yes, there are some common facilities that get reused as you're doing that, but you're really hopping from place to place to place. And if you want to accelerate that, you need to compile lots of code, and you need to be able to compile it fast, because you're not going to be there very long on any of those components. And mostly, if you spend a lot of time trying to do a very good job of compiling code, you won't get a payback for it, because you're going to finish initializing the component and never run those methods again. During ramp up, as I mentioned, now you're handling customer transaction workload. That's not the same methods that you were just initializing. They're completely new methods that are going to be handling those transactions. And here, we have a really hard trade-off, because these are the code paths that are going to matter at steady state, so we want to be able to compile them well, but the longer we take to compile them, the longer it's going to take to get to steady state. So this is where you really start to see the tension between trying to optimize for steady state versus optimize for ramp up. And obviously for throughput and latency kinds of performance, you really want to focus on getting the highest quality compilation that you can, which takes all of the work that you get to compile things aggressively, means more overheads, means slower ramp up, slower startup, etc. So how are we going to deal with all of this? As I mentioned, so hopefully I've convinced you here that there's a big problem here for us, and that we have to deal with all of this different stuff. And like I say, any one of these that we don't improve for somebody, there's usually an important enough person in the IBM scale of the universe, there's usually an important enough person who's going to go and complain about this. And since neither Vijay nor I like talking to executives about problems that need to get fixed urgently, we have a strategy that we've been investing in for a number of years to try to avoid that pain. And so in this talk, we're going to try to talk about how it is that we efficiently provide uplift for all of these different variations. And the benefit of our team doing this is that by providing uplift for all of these applications by our team, it means that all of the products and services and our customers' code that works on top of it, all they have to do is focus on their business problems. They don't necessarily have to focus on the performance issues of the Java runtime itself. And so hopefully you've seen in here some part, I'm not expecting everybody in the audience to have the same scale of problem that we have at IBM, but hopefully you see some part of this which resonates with what you're facing in your organizations. And because Semru runtimes are available for everyone to use, maybe you'll see something in the rest of this talk that will be useful to you and that will help you in your worlds. So just to level set here, what are we actually trying to achieve here? If we had the best of all worlds, what we would really like to see is 0 startup, infinite ramp up, and then the highest possible responses per second for all of time. And we would want to do that with the lowest possible memory use and the lowest possible CPU consumption, right? Fantastic. Let's see how we're going to do that. How close we can get. So in our strategy for approaching this problem, basically we've been driven by stakeholder feedback. So there's the famous quote from the philosopher Plato, necessity is the mother of invention. Our customers and our stakeholders force us to figure out how to solve this problem, and so that's where we've gotten to. And so what we're trying to do here is address all of the needs across all those different variations that we talked about. But our primary focus here on this talk is going to be on that performance metric side rather than on the variations due to deployment technologies, et cetera. Although it does factor in because obviously as workloads are moving to the cloud, things like containers, Kubernetes, et cetera, become more important, and we have to make sure that we're working well in those environments. All right. So there's some early positioning work that we did here for Java cloud optimization that we didn't actually do for the cloud because a lot of this work was done 15 or 20 years ago, but it put us in a really good position to be able to move forward in the world where cloud workloads are important. And the first one I wanted to talk about that is, so the problem, as I stated, was kind of this tension between the startup and ramp up compilation workloads and the steady state workload, right? Like how do you get to peak performance without slowing down your ramp up too much? And so to do that, we use in Semru runtimes a flexible, multi-tiered, we've never called it that, but that's what it's called in the Java universe, so we'll use their term, multi-tiered compilation technology. It's very adaptive. It's known as, historically, as the Testarossa JIT, in homage to the very fast sports car, and the fact that the person who originally designed it had red hair. And Testarossa in Italian means redhead, sorry, just in case you didn't know that. So if you look down the middle of this diagram, it shows kind of the different optimization level at which we can run code. Now the first one's interpreted, so obviously that's not compiled at all. That's the default way that you would run every method in the JVM if you didn't have a JIT compiler. But then there's a sort of temperature-based sequence of trade-off between how much time we're going to spend compiling the code versus how much expected payback we're going to get. And as you can see on the left-hand side, as you go down the chart, we're expecting performance to increase, right? Because we're getting hotter temperatured code, but the compile costs are also going to increase. So it's a way of trading off how much we spend for how much we expect to get. And during startup and ramp up, we can use compilation levels like cold and warm more. And as we get further along, we can use warm, hot, and even scorching if things are really consuming a lot of CPU time. Now we use a lot of heuristics to decide how to compile code at each of these levels. Some of those are embedded in the code themselves. Some of them are alongside in the runtime watching how the methods are executed. We have a sampling thread, which is watching how the code is running. And we leverage the class load hooks and all kinds of things to try and figure out how to how to move methods between all of these different levels. But I'm not going to talk about that because it's a very complicated topic. I do, however, want to talk a little bit more about the Testarossa JIT. This is an eyesore chart. Do not try to read this. The point I'm trying to make with this chart is that Testarossa is an extremely flexible compilation technology that was built basically in 1998. And we've used it for a number of different languages, to compile a number of different languages, probably more than a dozen at this point. Some of those have been production compilers, some of them have just been prototypes. It's targeted a huge variety of platforms for a huge number of different compiler products. We deal with a large number of performance metrics and have had to trade things off. And you know, there have been sort of on the left side, there is a long list of some of the really big investments that we've made over the years. This is not a complete list by any stretch, but it's been around for a very long time and we've been very successfully using it in a number of situations. And just one fun fact is that IBM has actually built more than 5 completely different substantial Java compiler technologies over the years. In fact, I showed at the bottom here, there's a list of, you know, from 1996 to 1998, we started building and have built 5 different compiler technologies. Some of them are research compilers, some of them are research compilers that we then productized. Some of them have been productized for a long time. Some of them did static compilation for Java, some of them are JIT compilers. But it's been a very interesting space for IBM. Testarossa was built by a production compiler team that existed already in the 90s. All right, so let's start shifting into that third part of the talk where we talk about, you know, some of the things that we had to deal with and, we already did that. The second problem that we're going to talk about is frugal memory use. So the problem here, Testarossa and J9 grew up for, you know, originally for Java in the embedded space. And in the embedded space, the devices that you have to compile to, especially 25 years ago, did not have very much memory, right? And by not very much, I mean like they could have a megabyte or maybe 2 megabytes of memory. So it's an extremely small space. Now, you're not trying to run a large application in that, but it does put pressure on how you design your data structures and how you design a JVM to be able to fit into that kind of space and still run a useful Java application. On top of that, as we started growing our embedded space JVM technology into the JVM technology that we use for all of our enterprise software, we ran into the complete other end of the spectrum, which is, you know, 15, 20 years ago, people were building massive, huge, commerce portal sites that were like so big it's hard to even imagine. And these put a lot of pressure on how much memory, like they wanted to use lots of memory, but the systems that you built didn't have that much memory, or it was very expensive to provide that much memory. And so it put a lot of pressure on us, again, to be small. So there are a number of things that we invested in here to try and make Java run in less memory than it otherwise would. So the first part is that we spent some time thinking about how to break some of the fundamental data structures within the JVM into RAM and ROM parts. So read-only parts that can be shared versus things that have to be writable at runtime. So by separating those out and putting them all together, it means that you can share entire regions of memory if they're read-only. Whereas if you have them together, then they're kind of interspersed and you can't really effectively share the code. Now classes are the best example of this in J9, but it's not the only one where we've done that kind of a split. One of the ways that we've exploited this is by putting the ROM parts of classes into a thing called a shared classes cache, which Vijay is going to talk a little bit more about in a minute. But I'm not going to. A second thing that we did a very long time ago was move to a single word object header, which allows us to reduce the size of our live object data, right? It means that you don't pay as much of an overhead to have a Java object as you would in other JVMs, which might have 2 or 3 word headers. Especially if you have a very small object, right? You might have 1 field in it. If you have to pay 24 bytes of overhead to have an 8-byte field, that's a lot of overhead. So if you can strip that down to having only a single 8-byte word, then that's great. We also use compressed references. Now, this isn't a unique feature, but we use it too, to compress heap pointers so that even if you're running in a 64-bit process, we can represent them on the heap as 32-bit pointers. And we use some shifting and trade-off object alignment. So you can't have an object at an arbitrarily aligned address. We align objects at, say, 8 bytes or every 16 bytes. And that allows us to shift bits down and get extra bits at the top so we can represent pointers on larger heaps. It does obviously incur some costs because you have to decompress pointers before you can use them. You have to compress them when you're storing them. But the trade-off in terms of being able to use 32 bits consistently across the whole process saves a lot of memory, so it's a good thing to do. It's dynamically determined based on the maximum heap size. Finally, the heap growth heuristics that OpenJ9 uses are very sort of dampened based on how much overhead the GC is incurring. And the idea here is that usually one says if you want to increase throughput, you make your heap as large as you can. But there's a trade-off there. It's like you don't need to go all the way up to as big as you can because you'll get diminishing returns as you make the heap size larger. And so J9 tries to only slowly creep up the size of the heap before it will, only until it gets to a sort of acceptable level of GC overhead. And that way we can provide throughput without necessarily consuming all the memory that we would otherwise. Now, unfortunately, we found, we used to give out some of this advice ourselves a long time ago, that there's lots of advice out there that says, if you want performance, set the minimum heap size and the maximum heap size to the same value, right? To force it to always use the largest heap possible. And it's true that does maximize your performance, but it also basically kneecaps this facility of OpenJ9. So we've had, lots of people have read the sort of standard advantage that OpenJ9 or Summer Runtimes claims that we can run your Java workloads in half the memory. But if you're telling it that it can't change the size of the heap, then you've kind of eliminated the way that we would provide that memory advantage to you. So be careful about that. Make sure that if you're going to try out Summer Runtimes, you haven't used it before, try to get rid of that -i or reduce the size of your -XMS and give OpenJ9 some flexibility to be able to reduce the size of your process. All right, and with that, I'm going to pass it over to Vijay, and I'll come back later at the end.
Thank you, Mark, and hello, everyone. So Mark briefly touched on this technology called shared class cache, and he touched on it in the context of memory footprint. But I'm going to talk about it to give you just a little view into what this technology is, because it's key not just for memory footprint, but also for startup time. So the shared class cache technology is really easy to understand. It's basically conceptually, you run with this -x shared classes option. You create a file on disk. The file contains a bunch of useful stuff. So useful stuff could be read-only portions of classes like bytecodes, ahead of time compiled code, some other information, hints, etc. that the JVM decides to put in there. So you run the JVM once with this option, the file gets created. Next time you run the JVM, again with the same option, it transparently, it sort of works, it detects that there's this file on disk. It has all this useful information in it, and it just picks that information up and starts using it. So basically, you don't have to repeat some of the work that you did in that first run. If classes were already put in there, they were initialized, they were verified, you don't have to repeat that. If ahead of time compiled code was created, you don't have to JIT compile that code. So there's this notion of cold run versus warm run. The cold run populates the cache, it's the first run. The warm run, or warm runs, pick up from the cache and start using it. The most important artifact that we put into the shared class cache is the ahead of time compiled code. Ahead of time compiled code differs from JIT compiled code in that it is reusable across different JVM instances. So we generate the AOT code, again, transparently during startup time. So just as we're populating the shared class cache, we're generating AOT code. We put it into the cache. And then when we load the AOT code out of the cache, that is about 100 times faster than doing a JIT compile, because the work has already been done. The code is sitting there, you just need to pull it into this invocation of the JVM. Now, AOT code differs from JIT code, as I said, because it needs to be reusable across JVM runs. So it's slightly more generic code than JIT code is, but it's only slightly less optimized, and it really doesn't matter in the end because the JIT is capable of recompiling and getting up to peak throughput anyway. So that's great. We achieved fast startup time using the shared class technology. We talked about creating a file, reusing it in subsequent runs. But then if you're running in containers, all this sort of flies out of the window because you create a file, you're running inside containers. Now the container goes away, the file goes away along with it. how is the subsequent run going to come along and take advantage of the cache? So you're only paying the cost. Every run is a cold run, and you never reap the benefit. So this is where this solution that we came up with comes in. This is embedding of the shared class cache in containers. So basically, you need some form of persistence. You can't let the cache come and go with the container. So in order to get persistence, there's a couple of alternatives. You can use shared volumes. You can put the cache basically outside the container so that it lives and is independent of the lifetime of the container. But this is quite cumbersome. I mean, you may be running your workloads across a large cluster. You don't want to be provisioning shared class caches for every application across this cluster on many different nodes. It can get out of control fast. So the solution that we came up with was we decided to embed the shared class cache in the container images themselves. So the cold run that I talked about earlier actually happens at build time. So when your container image is built. So what we have to do, though, in order to take advantage of this is when you build your container image, you have to start and stop your application. So when you start and stop your application with the xShared classes option on, it produces the file which has all the cache contents, and then you can embed that cache in the container image. We've also re-architected the shared class cache to mirror how container layers themselves work. So there's a multi-layer shared class cache. Basically, what that allows you to do is to ignore every other level and what it did when you build the shared class cache at your own layer. So you can build a layer at the JDK layer. You can add one at the framework layer. So Liberty does this already in the images that they ship. Tomcat or other layers or other frameworks could do this if they went with Semaru JDK. And of course, there's the application itself that sits above the framework, and you could add classes and AOT code at that level as well. Because all this population of the cache is happening at build time, it's actually, you don't need to worry about adding to the cache at runtime. So you can run with this read-only option that we have in shared class cache that allows you to access the cache constituents quickly. We're going to get to some results quickly, but just in true software engineering style, when we solved a problem with embedded shared class cache, we also created one. Namely, now you have to do this build step. You have to add AOT code. You have to add shared class cache during your build step. Well, the build environment that you're building your container on could be quite different from the deployment environment that you're going to run your container in. So if you're putting in code into the ahead of time compiled code into the container image, how are we accounting for the differences in the build environment versus the runtime environment? Well, there are different aspects of differences here. The build environment versus the runtime environment, you can have differences in the architecture level of the machines that you're running on. Maybe you're building on a new machine, but you're running on an older machine. In that case, an example would be that you can crash if you're building on a newer machine and then running on an older one, because your code may have used some instructions that are not available when you run in the deployment environment. There are also some other aspects of this that we take care of transparently in the JVM. So you can change your heap size between the build environment and the run environment, and we can handle that. But there are other more fundamental changes that we can't handle. So if you change the GC policy entirely, we'll just stop using the AOT code. At that point, the application will still run, but we won't use the AOT code anymore. This option to generate portable AOT code is enabled by default in containers. So it enhances the out-of-the-box experience if you're running in containers. And the performance overhead from using portable AOT code isn't that significant. So we talked about embedding a shared class cache in the container. Let's now look at some results to see what that achieved. So you're going to have to get used to this format because we're going to show this a few times throughout this presentation as we talk about other technologies that are coming up. So I'll define some things as we go along. First of all, this is a Java EE application called Acme Air Monolithic. So this is no toy application. Let's focus on the startup graph that's on the top left. The gray bar is running without any shared class cache in the container. So lower is better because this is startup time. So you can see startup time is quite slow. Then we show the red bar, which has a shared class cache embedded in the container, but only at the JDK layer and only at the framework layer. So its startup got a little bit better, but if you look at the next bar, which is the blue bar, That one is the full shared class cache. So we built the shared class cache in the entire application image. We have all the classes that we could possibly want to cache. And now you take a look at this startup time, it's almost half of where we started. So the embedding of the shared class cache really helped with startup time in this case. And the fourth bar there, the orange one, is running with the full shared class cache, but not embedded in the container. It's actually mounted on the volume. And in that case, because classes are being added throughout the run, we can't run with the read-only option. So the startup time isn't as good as when we embedded a full shared class cache and it was read-only. Now let's look at the graph on the top right a bit. That shows throughput, two forms of throughput. Throughput in the first 5 minutes is really indicative of ramp up. And you can see that throughput in those first 5 minutes was best with an embedded or with a shared class cache that was mounted on volumes. This is because we were adding classes to that cache throughout the run. And so we were able to improve our ramp up in subsequent runs with that shared class cache. And last but not the least, at the footprint graph shown at the bottom, you do see a slight increase in memory footprint when you're using the shared class cache. This is because there's a little bit of duplication when you're using the cache. There's code in the cache as well as in the running process, and that adds to our footprint a little bit. Now we show the same result running across 8 pods. And all of the trends are basically similar, except that when you're running 8 pods, in general, throughput is affected or performance is affected because there's more pods and they interfere with each other. This also serves to dampen some of the differences between the configs. So we no longer have as much of a ramp-up advantage in this case. Now, in this case, there's also another effect that takes over. If you have multiple pods running on the same node, there's sharing across those pods. There's memory gets shared across those pods. So even though you have more memory being used with the shared class cache, the fact that there's more sharing across the pods means that the difference between no shared classes and shared classes cache actually reduces. Okay, great. So we saw some results. Embedding a shared class cache really helped with startup time. It's fast, but not fast enough if you want to be running scale to zero and serverless use cases. So this is where this very recent feature that we added called Instant On comes in. Instant On is a feature that uses the Linux CRIU capability, or CRIU stands for checkpoint restore in user space. What this is that we'll be able to use the Linux CRIU technology to be able to start an application in milliseconds instead of seconds. If you look at the graphs back here, this application is starting in about 5 seconds in the best config. But if you want to start in milliseconds, that's where Semeru Instant On comes in. So the basic idea, again, is very, very simple. You run with this CRIU capability. You take a snapshot of a running process. You bundle that snapshot into your container image at build time. Then you take that container image with the snapshot and you run in the deployment environment where the JVM detects automatically that, oh, hey, this checkpoint exists or the snapshot exists. Let me restore from it and speed up startup. So why does Linux CRIU checkpointing help with startup time? This is because basically you run the application up to a certain point, you take your checkpoint. At that point, you capture all the state that that process had. All the memory pages, all the file handles, etc., are captured in files that are persisted on disk. Now, when you run CRIU and restore the process, what happens is the process comes back to life from all that information that was stored, but it comes back to life picking up from where it left off. So you don't need to repeat a bunch of work that you had done earlier. And that's how this startup is really fast in this case. A lot of work in Instant On actually hasn't been around performance because just this model achieves super fast startup anyway, but it's been about usability. So it's around shielding the end user from the complexities of Linux CRIU. And the best way to do that is actually to build a function not just in the JDK, but also in a framework that sits above the JDK, so that the user doesn't need to worry about all this. It's dead easy from their perspective. They just bring their application, they come here and say, I want to use this feature, and that's it. So some of the advantages of this approach versus the native image approach that you may have heard about, there's full Java support. Once the process has been restored, it's like any other normal running Java process. It does achieve super fast startup, as those results at the top show. There's also peak throughput. There's no throughput cost. Unlike with native image, where in some cases people have reported like a 30-40% throughput drop, with instant on, there's no throughput drop to speak of. And it's very competitive from a low memory use, et cetera, point of view, as we will see in the results that are coming up. So one more slide on how this is all managed and achieved. There are several things that are added by Liberty and Semeru Instant On. So before getting into that, I should define what Liberty Instant On is. So the Instant On capability at the JDK layer is what we refer to as Semeru Instant On. The framework, we modified a framework or collaborated with a framework above us to make changes as well. That framework's name is Liberty, and the feature at that level is called Liberty Instant On. So the first thing that we did was we created an API that was a wrapper for Linux CRIU, because we don't want Java processes to be directly working with this low-level tool. So we have the CRIU support class that is basically the Java wrapper for native CRIU. This class is offered up to the Liberty framework, which calls APIs through this class in order to control the CRIU. It can say, I want you to take a snapshot here at this point. And then the user application sits above that, and it does not need any awareness of CRIU at all. It doesn't even need to know that this technology is in play. There's various compensations that are done by the app server and the JDK working together in order to make this a seamless experience from an end user perspective. Some of the things that we fix up, for example, are we allow you to specify environment variables at runtime. We allow you to run your applications and not worry about security. We clear out all the security state from the checkpoint because you don't have to worry about shipping a checkpoint with your container image. We've already stripped away the security state from that. And many expected behaviors, like if you use a random number in your program, you want that to be a random number generator across all the different container instances. So we take care of all this transparently. This is done in the JDK and the app server. So enough talk. Let's show a demo of this feature in action. So first of all, I'll show you the demo with Liberty Instant On working on top of Semeru Instant On. So first things first, let's build some containers. Let's build a container that is the baseline container. So this is just the script that I have to build a baseline container. All it does is uses Podman to build this getting started application. That's a simple Java EE application. And it's just going to use the Docker file in this directory to do that. So let's see what's in that Docker file. In that Docker file there's only 4 lines here. You're pulling from this Liberty Beta Instant On image. You're copying in the application files into the right directories in Liberty, and then you're running a standard configure script to configure that application. Very, very simple setup for the baseline. So let me run this script so that we're building that base container image. And then let's shift over to looking at how to build the Instant On image. So this is also very, very simple. There's just one line in here. The image that we're building is tagged differently, getting started Instant On Devnexus. Notice that we need to pass in some Linux capabilities into this podman command because the CRIU utility needs these Linux capabilities in order to do its work. We also used a different Docker file here. The Docker file that we used was dockerfile.instanton. So let's take a look at how that one differs from the original. Again, it pulls from exactly the same place, the Liberty Beta for Instant On. All the other steps are the same, except we added a 5th step. So here, that's all that the user needed to do, really. We added a 5th step saying, please generate a checkpoint for me using this checkpoint.sh script, and I want you to generate it at the applications phase. Liberty offers the option of creating a checkpoint of one of 2 phases, deployment or applications, and in this case, we're picking applications. So let's go and build the Instant On container next. So that while that's going on, let me check up on the original. Yes, that baseline container is built now. Before we jump in and start running that, I'll show you how we're going to run it. So that's, again, a simple podman command, which is just going to use the container image that presumably just got built. So let me check if it did build it. So in this, the most recent one that you'll see is this getting started Devnexus that was just built a few seconds ago. So that's the one we'll be using. When the instant on image is built, we'll be using that one. And that one, again, has a simple podman command to run the image that we're building. We'll check on it in a minute. And we pass in 2 Linux capabilities to it. This is the minimum set of 2 capabilities that you need to pass in, this checkpoint restore and set pcap. That's it, very simple scripts. Check up on the other window where we were building the instant on image, and that's done now. In fact, if you check what we requested was at the 5th step, we said, please generate a checkpoint, so it's honoring that. In fact, if you look here, there's an error message or a message that comes out saying a server checkpoint was requested and now has been created. So we have the 2 images. Let's now run those images and see how it performs. So the baseline image first, we'll run that one. The server is starting up. This is the Liberty server starting up. And in this case, it took about 5 seconds to start up. If you look at the time here, it says 5 seconds. So let me try that again. It'll take probably 5 seconds, approximately that amount of time to start up the server again. Just give it a couple more. Yeah, approximately 5 seconds. So great. Now let's run the same application except with the instant on container image that we had built earlier. And in this case, you see the output first. It says resumed operation from a checkpoint. And if you look at the time that it took us to start up, 0.226 seconds. That's an order of magnitude faster than what we had before, 5 seconds to 0.2 seconds. Truly matches the description of instant on. So again, this tried it again, and it's 0.2 seconds this time. So this is the instant on in action running on top of the Liberty framework. So let me switch back now to the presentation and get back to that slide that I showed earlier with results, except this time we have instant on added to the picture. So cleared out some of the other results around shared class cache experiments, just showing the no shared class cache and the best config from a startup time perspective before instant on. But with instant on, you can see this is an actual Java EE application. I should emphasize that you're able to see an order of magnitude faster startup. And this happens basically with no harmful consequences at all. Every other metric is left unaffected. Same result shown on 8 pods. And in fact, there's a slight improvement in footprint that if you see the PSS shown at the bottom there, that's the proportional set size. So PSS, proportional set size, says that accounting for the non-shared memory that a process uses, but also for the shared memory, you're accounting for the sharing. So if 3 megabytes of shared memory was used, you would only count 1 megabyte of that towards the process if you were sharing it across 3 processes. So there's a slight decrease in the PSS that's used with instant on. And this is because there's some cleanup that we do before we generate the checkpoint. And this lowers our memory use as well overall. So great, we spent a lot of time talking about startup time. Now let's shift focus and talk about ramp-up time and memory footprint as well before we conclude here. So in order to improve our ramp-up time and memory footprint, we have this feature called the Semeru Cloud Compiler. And what is this feature about? Basically, it takes this component in the JVM called the JIT compiler and decouples it from the JVM and runs it as an independent process. So first of all, what is a JIT compiler? It is this component within a JVM that generates code and improves your throughput performance, basically. If it weren't for the JIT compiler, your throughput would be 1/10 of approximately of what it is today. So it's very, very important. The job that it does is very important, but it takes a lot of CPU and memory in order to do that job. And the basic idea of the cloud compiler or the JIT server is to offload all that work to a remote process. In fact, you can create a separate pod, a service with the JIT server altogether, allowing these JVM clients to connect to the JIT server, request compiled code. So it's a bit of a client-server model going on here, but basically the JIT server has been pulled out of the JVM. And what this means is it's a bit like thinking about the JVM itself as having been changed to a microservices application. So it used to be a monolith where the JIT compiler was in there. Now it's been refactored in this way. So what are the benefits of this approach? You don't have to think about the JIT compiler. You don't have to worry about this other component that's there that you don't understand. It's been removed from the process or removed from the container. So you can size your containers more easily because you understand what's in the container now. It's only your own application. And so you have a better understanding of it. It could also only be a smaller container. You've removed something that used to be inside the container. It's also better from a resiliency perspective. In the unlikely event that the JIT compiler crashes, the JVM would come down if it was in process. If you pull the JIT compiler out of the process, even if the JIT compiler crashes, the rest of the JVM does not come down. You can still communicate and reestablish a connection to the JIT server when it comes up. So what are the benefits? So in this case, in this graph, we show 3 configs, the same application as we've been seeing all along, Acme Air Monolithic, running in a 400 meg container to begin with, achieves pretty good throughput. Same thing run in a 200 meg container on the top right. It doesn't achieve as high throughput here. It struggles to get up there because the JIT compiler is working hard trying to stay within the memory envelope that has been given to the container. Only 200 megs are available to it, so it becomes conservative and cuts corners, and so your throughput doesn't end up being as high as it was. But the curve shown on the bottom, this is 200 megs, so a smaller container, but with JIT server. And you see not only peak throughput, but you also see us getting up to that peak throughput very, very quickly. So we ramp up really fast in this case. This is because the JIT server is remote. It has more CPU allocated to it. It's able to ramp up and churn out more compiles quicker than if it was inside the process. So you ramp up to equal throughput as you had with 400 megs, and you do it much more quickly. This graph provides the same duration view, except for memory footprint, so the RSS over time. You see that with 400 megs, there are all those ugly spikes that come up. That's the JIT compiler working hard in order to generate better code to improve your throughput performance. Imagine if you had those spikes and you had to size your container larger just to account for those spikes. On the right, you have the spikes are much smaller because there's only 200 megs available. So JIT compiler doesn't use as much memory. It's sort of damping itself down. But if you look at the graph at the bottom with JIT server with a 200 meg container, it's super smooth, primarily because the JIT compiler is not even there. So there are no spikes. This is just the application, the Java application using memory as it would normally. So very, very smooth curve in this case. Of course, there's still the view on the server side where the JIT server is running, and this is the view on that side. You see that there's a lot of CPU being used. There's some memory being consumed when it's doing its work. So you may be wondering, well, we just took memory and CPU that was used in the container and moved it from here to there. But that's not actually the case. That's not the point. The point is that there could be multiple JVM clients connected to one JIT server. And over a long period of time, these could be interleaved. So yes, you did move the memory from here to there, CPU from here to there, but you don't need to size the JIT server to be this humongous container. You can size it moderately and have a bunch of smaller client JVM containers sized really, really small. So you can save cost because there's more client containers, more client pods than there are server pods. And now this is the final wrap-up view with this feature as well added to the mix, again for the same application. You see the fourth bar, that's everything combined. The startup time is obviously quite good in this case because it was already quite good with instant on. But if you look at the throughput in the first 5 minutes, that's basically our estimate of ramp-up time, right? As the application was coming up, how much throughput were we able to deliver? And this is clearly higher with JIT server, because the JIT server has more resource. It's able to ramp up the application faster, as we saw on the previous slide. And then the other thing to note is the graph in the middle and the bottom. That's the peak RSS. So the peak memory went down dramatically with the JIT server because the peak memory was actually being consumed by the JIT. Now that the JIT is outside the container, the peak memory usage goes down dramatically as well. And all in all, if you look at this situation across all these 8 pods, what you can see is, compared to where you started, shared class cache not working inside containers, we showed all of these technologies, and you saw startup time go from almost 15 seconds down to under a second, so dramatic reduction in startup time. pretty good improvement in ramp up if you measure it by the throughput in the first 5 minutes. None of these things penalize the throughput a lot. The peak throughput is more or less what it was all along. A very significant reduction in the peak memory usage, as you see in the middle graph at the bottom. And all this without compromising on the basic usability of Java, right? Like we're still running a Java EE application here. All the capabilities of that Java application are in effect. So we really made a material difference here in a full Java EE application without hurting any metrics. So we didn't leave any workload behind. We're running significantly complex workload here, and we also didn't leave any metrics behind. With that, I'll turn it back over to Mark.
In the interest of time, I'm actually going to skip this slide. Feel free to talk to me later about future directions and things we're hoping to do next with this work. But I want to wrap up with a summary of basically what we covered today. So we talked about summer runtimes, the JDKs that are used to support IBM's business. They're available freely for everyone to use. And we talked today about how we've been investing in summer runtimes to design them to run in the open all kinds of Java workloads and deliver excellent performance on a variety of metrics for private, public, hybrid cloud, wherever you deploy your stuff. It's the only Java distribution that uses Eclipse OpenJ9, and that's what enables a lot of the performance improvements that you were seeing in the previous set of slides. We've spent a lot of time thinking about different techniques that we can use to improve metrics in different ways. And as you saw, some of the techniques that Vijay was going through have their pros and their cons, right? They would improve one metric, but maybe not another metric, or they would go in opposite directions. And so it's important to take away from this that there's no single silver bullet tool that you need. You need to assemble a set of things that can mitigate each other's weaknesses and deliver that final performance, close to that ideal performance that I was showing. I don't think we quite have achieved that yet, but we're a lot closer than we were when we started. So, we talked about a number of different tools. I'm not going to go through that list, but by combining them, even a monolithic Java application, right? It's something that's, you could characterize that as being at the very beginning of its journey to cloud. In hundreds of milliseconds in the smallest containers that you possibly can, with very good ramp up and excellent peak performance. So, in summary, I guess IBM Summer Runtimes are built to make Java run better in the cloud, leaving no workload behind. And hopefully, you saw something in this talk that can help you. Thank you.